Hello everyone and welcome back. My name is Mr. Kovalt, and in this video I'm going to be going over a particular situation in which the equilibrium constant is small and you're starting with lots of reactants. So as I said in a previous video, I want to go over how to understand your equilibrium constant and how to use that understanding to help you figure out problems and solve problems that involve an equilibrium, and whether or not you can neglect the change in X using your ICE table, and whether or not you're going to be using or would need to use what is called a stoichiometry table or an ICF table first in order to solve the problem. And that is something that I've seen students struggle with, is trying to determine, like, do I use an ICE table, or do I do a stoichiometry problem first and then do the ICE table? How do I figure that out when I'm looking at a particular problem? And let me start by saying from the very beginning is the way you figure that out is by looking at your K value and then determining what that K value means with respect to the amount of products versus reactants at equilibrium. And on top of that, in addition to that, you need to figure out which way it's going to shift. So generally speaking, the way you want to think about this, the rule that you want to use is that if your reaction is going to be, if not is not at equilibrium, and it shifts towards the side that is not favored, then you can use your ICE table, and then you can neglect X, right? So you can do the X is small approximation. You can get rid of the X and simplify the calculation and find your change, right? But again, anytime you use the X is small approximation and neglect X, you have to do your 5% rule calculation to make sure that is within the 5% margin of error. And if it is, then you know it's a valid assumption to neglect X. And then if it's not, then you have to go another route, like using the quadratic formula or using the method of successive approximation or something like that in order to solve the problem. But in this video and other videos, I'm going to show you how do you determine whether or not you can right away use your ICE table and then use your X is small approximation to neglect X, or if you need to use if you need to use a stoichiometry table or an ICF table first before doing your ICE table. And again, the rule of thumb is going to be that if your reaction is shifting towards the side that is not favored, then you know you can use the ICE table, because if it's shifting towards the side that's not favored, then you're going to get a tiny amount formed on that side. And so if you got a tiny amount that's being formed, chances are you can neglect that change, right? Um, on the other hand, if your reaction is going to shift towards the side that is favored, then you know a lot of it is going to change that direction. And so you can't assume that X is small in that regard. And so if it's shifting towards the side that is favored, the best thing to do first is to assume that it all shifts that way. Do your stoichiometry to figure out what amounts you have after you shift it all the way to one direction. You're going to have to do a limiting reagent type problem to figure that out. But once you figure out the stoichiometry in the final stage, then you can take those final amounts after the stoichiometry and then do your ICE table using those amounts as molarities to start your ICE table in the initial part. So again, I know I'm talking a lot in this introduction, but I'm going to be going over this in separate videos coming up. But in this video, I'm going to be focusing on K is small, and you're starting with a lot of reactants. And so in that case, what do we do? How do we solve this problem? So let's get into this. So the situation we're in is we have a problem in which K is very small, and we're starting with a lot of reactants and very little product or in other words, we have zero product. And so in that case, we know that here in this equation, here's my generic equation, and it doesn't matter what the equation is. I'm going to use a generic one, but this applies to any reaction that fits these conditions. And so here's my generic equation. And for this generic equation, I have an equilibrium constant that is 4.0 times 10 to the negative 8. I don't know if you can read that. That's an 8, not a 5. So negative 8. Let me fix that so it's clearer. So this is a negative 8. I think that's better. And so obviously that's a very small K value. And what that means is, again, we have to understand what this K value means. It means very small K means you have very few products and a whole lot of reactants. And so the equilibrium is favoring the reactant side. Okay? So that's the first thing I need to keep in mind. So my reaction equilibrium is favoring the reactant side. Now I have to figure out which way is it shifting. So here, since I have zero product, according to Le Chatelier's principle, right, it's going to shift in the direction in order to make product. I can't have zero product at equilibrium. Some product must be there. So it's got to shift to make more product. So I know for a fact it's going to shift in this direction. Okay. So is it shifting towards? So the question I want to ask myself is it shifting towards the side that is favored or towards the side that is not favored? Since I know from the K value, the KEQ value here, it's really small. I know the side that is favored is the reactant side. I have a lot of reactants at equilibrium. So this side is very much favored. So I know it's shifting away from the favored side. It's going towards the non-favored side. And in that situation, if I have a reaction that is shifting towards the non-favored side, I can go ahead and do an ice table, and then I can do I can neglect X and do my X's small approximation and do my calculations that way. So I know I can just go ahead and do an ice table here. I don't have to do stoichiometry first. I can just do my ice table. So let's go ahead and do that. So here's my initial conditions. So what's the change? So I know it's shifting this way. So that's going to be a negative 2x. And it's a 2 there because of the coefficient. I have to do the stoichiometric amounts. So I'm going to lose a 2x amount here. This has a 1, so that's going to be a minus x here, 1x there. And then on this side, I'm losing it, but this side I'm gaining. So here I have a 1 and a 1, so I'm going to have a plus x amount here, plus x amount here. I'm going to add these together to get my equilibrium. So this is going to be 0.50 minus 2x. Oops, I almost wrote x. So that's going to be 2x. And then here I'm going to have my 1.00 minus x. And this is just going to be x. And this is going to be x. So now I have my equilibrium amounts in my ice table here. So now I can set up my K expression for this reaction. So KEQ is equal to the concentration of the products. So concentration of C multiplied by the concentration of D raised to the 1 power. We don't write the ones. And then I have my reactants on the bottom. So since I have this 2 here, that means the concentration of A is going to be squared, raised to the 2 power, multiplied by the concentration of B. And so that is the K expression. So now I can plug in my equilibrium expressions in terms of X. And so that's going to be equal to, so C and D, the concentration of C and D. So that's going to be X times X over, and then I'm going to put these in for these. So this is going to be is going to be 0.50, 0.50 minus 2x multiplied by this here. Oh, and don't forget the square there. So this should be squared. That's important to not forget. And then I'm going to put in this for the concentration of B. So that's going to be 1.00 minus x. Okay, let me make sure I have my equation right. Yep, that is correct. Okay, so I just wanted to verify I was using the right equation. Okay, so now this is my x, my equilibrium expression in terms of x. Now, this is where I can neglect x, right? So why can I neglect x here? Because I know that it's going to shift in the direction that is not favored. So if it's shifting in the direction that's not favored, then I'm going to get a very tiny amount shifting in that direction because it doesn't want to go in that direction, right? It favors the reactants. It wants a lot more reactants compared to product. So if it's going to shift in this direction, it's only going to shift a little tiny amount. So I can assume that it's going to be a small enough amount that I can ignore because subtracting this from 0.50 is really not going to affect the amount. It's going to end up being very close to 0.50 again, right? Maybe it's 0.59999, right? So that's very close to 0.50. So if that's the case, then I can ignore these. Now, I don't necessarily know if that's the case. I have a very good hunch that based on how small this is, that it's probably most likely going to be valid, but you always want to do a 5% rule check at the end when you solve for x, and I'll show that in a moment. So given that I know it's shifting towards the side that is not favored, I can assume for the moment that x is going to be so small that I can ignore it. So I can eliminate x here because subtracting x or maybe even adding x is not going to affect the amounts here and here. So I can get rid of the x here. Notice I'm not getting rid of the x's here because I'm not subtracting or adding x to anything. It's just sitting there. So I'm not allowed to get rid of those. But I can get rid of these since, again, I'm subtracting the x amount and I'm supposing that this is so small that I can just ignore it. So then that simplifies everything. So then this becomes x squared over, and then I'll have 0.50 squared multiplied by 1.00. And so that is much simpler to solve. And so I know that this is equal to this number here. So that's going to be 4.0 times 10 to the negative 8. And so now I can solve this for x like so. So if I multiply both sides by this and this, right? So then I get, I'll write that over here, I get x squared is equal to 4.0 times 10 to the negative 8. And that's going to be multiplied by 0.50 squared multiplied by 1.00, right? So if I stick that in my calculator, what did I get? I get, let's see, I don't have that calculator here. I can just calculate it right now. So on my calculator, okay, hold on. Okay, when you calculate that out, you get 1.0 times 10 to the negative 8. And then you take the square root of that. So if you take the square root of x, so the square root of x squared is equal to x. That's going to be equal to the square root of 1.0 times 10 to the negative 8 which then becomes 1.0 times 10 to the negative 4 molar. And so that is the change in the amount of stuff that you have going on in the shift. So this here is X, that's the change. So that you went from 0 to X, so that's your change. So now the next thing we want to do is do the 5% rule, which means we need to check to make sure our assumption here that we can ignore X or neglect X because it's so small, we need to make sure that that's valid. And then we're going to do the 5% rule. So how does the 5% rule work? Well, we have to compare the change that we have, compare that to the original concentrations that we have. And normally what you want to do is do the 5% rule for both concentrations to make sure that both of them fall within the 5% margin of error, right? So then I'm only going to show it once to give you an idea, but normally you would do it twice for each one, making sure that the 5% rule applies to both of the reactants. So how do you do the 5% rule? Basically, all you're doing is you're taking the change here that you got for X and then divide it by the initial concentration you got for the reactant and then multiply that by 100 to get the percentage. So then here I would take the 1.0 times 10 to the negative 4, which is the change that I got. That's my X value. And then I would divide that by the concentration. So here, since I'm using X, if you're doing this one, then the change is 2x. So you'd have to use the 2x amount to do that. But here I'll just use the x amount. So I divide that by 1.00 molar, right? Multiply by 100. And what do you get? You get, hold on a second. Actually, yeah, so you get 1.0. Oh, sorry. Let's write this way. So you'd have, yeah, 1.0 times 10 to the negative 2%. Or if you want to write it normally in standard notation, you'd have 0.01%. So that is obviously less than 5%. So our assumption here that we can neglect X is valid. So we can go ahead and keep this value for X and use it in our calculations. And we can plug them back into our values here and then determine what our equilibrium concentrations are. And so that is how you would do a problem like this. So anytime you have a problem where K is small and you're starting with lots of reactants, you can go ahead and do your ice table and then neglect X and solve the problem easily without having to do a quadratic formula that would require you to, solve for X. And so again, you would always do the 5% rule. Do the 5% check anytime you neglect X. But one thing I do want to say that a rule of thumb is that if your K value, if the K value you have is about 1,000 times smaller, on the order of 1,000 times smaller than your product, then the concentration of your reactants that you're looking at, it's a safe bet that your X value, that your neglect of X, that your ignoring of X is valid. It's usually, and then you can forego doing the 5% rule. But if it's like 100, a fold difference or less, then probably not. You probably want to check it. But rule of thumb is always check to make sure that your neglect of X, your ignoring of X is valid. And so this is the way you would do that. So that's it for this video. I hope you found this video helpful. If you did, please like the video, share the video, hit that like button. Also, make sure you subscribe to my channel, hit the notification bell. And when you do, make sure you click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me and have a great day.